Alright everybody, welcome back. This is video 2 of section 4 from unit 2 of AP Calculus, connecting differentiability and continuity, determining when derivatives do and do not exist. In the next segment of this section, we're going to talk about the types of non-differentiability that can occur, the common types of non-differentiability. The first one here, what's known as a corner. Corners occur where the one-sided derivatives are different and finite. One-sided derivatives are different and finite. So I'm going to go ahead and draw one. Let's see, there we go. We've got this point here. And let's go off this way. And this point right here is a corner. The derivative to the left of that point is 2. The derivative to the right of that point is -1/2. Those are both finite values, but they're different. And certainly answers to this question may vary. But they form a corner. It doesn't have to be a 90-degree angle. Of course, I drew one that was. But, any kind of corner will do. Any absolute value function, or any absolute value of a linear, that V-shaped absolute value, those all have corners. So that's what a corner is, what it looks like. A cusp. Cusps occur when the slopes of the curve as you approach a point approach -infinity from one side and infinity from the other. So here's what a cusp might look like. I'll put the cusp at this point right here. And coming to that, approaching that from the left, the slope is approaching -infinity, but approaching it from the right, the slope is +infinity. And so when these two meet, we end up having a cusp. We could also have a cusp in the other direction where, it approaches +infinity from the left and -infinity from the right. Alright, so that's a cusp. That's another kind of non-differentiability. Alright, next. A vertical tangent. And I mentioned in the last video that usually when we talk about functions being differentiable, that means they're smooth, so to speak. A vertical tangent is a situation where we have a curve that's smooth, but it's not differentiable at a point. Vertical tangents occur when the slopes of the curve either both approach -infinity from the left and right, or both approach +infinity from the left and right. This is not always easy to see on a graph. Let's do it at this point right here. From the left, the slope's going to approach +infinity, and from the right, it's going to approach +infinity. And so it might be a curve that looks like this. And right here, at x equals 3, for just an instant, the tangent line to that curve is vertical. Okay, now this is one that, you can see commonly in some relatively easy to express functions, odd root functions, y equals the cube root of x, or y equals the 5th root of x, or any of the curves like that. Those all have vertical tangents on them at the center of the curve. All right, and the fourth situation where we might be non-differentiable is a discontinuity. Okay, now it doesn't matter whether the one-sided derivatives are the same. If we have a discontinuity, it's still going to be non-differentiable. For instance, suppose I draw a curve like this. So even though the derivative from the left and the derivative from the right appear to be the same, this function is non-differentiable here at 2 because the curve has a discontinuity. Okay, so those are the 4 common scenarios where we have a curve that's not differentiable. Implications of differentiability. Differentiability implies continuity. If a function has a derivative at x equals a, then that function has to be continuous at x equals a. It's important to note that the converse of this is not true. Knowing that something is continuous does not mean that it's differentiable. We saw that with our cusps and our corners and our vertical tangents. All those functions that I drew were continuous, but they were not differentiable at their entire domain. But if I know that something's differentiable, it has to be continuous, and that's because a discontinuity is a cause of non-differentiability. And so this will come up for you frequently, on your AP exam, where they might tell you that a function's differentiable, and you're expected to know that that means that the function has to be continuous, and all the different things that we've learned about continuous functions will apply to that differentiable function. Another piece that follows from here, the intermediate value theorem for derivatives. Just like there's an intermediate value theorem for functions, there's an intermediate value theorem for derivatives. If a and b are any 2 points on an interval in which a function is differentiable, then f prime takes on every value between f prime of a and f prime of b. This is pretty much just the intermediate value theorem for functions, except now it's extended to the derivative, and instead of the function needing to be continuous, the function needs to be differentiable. But basically what it says is if I have a function that on a closed interval from a to b is differentiable everywhere, okay, then the derivative takes on every value between f prime of a, which is this slope here, and f prime of b, which is this slope here. And any slope in between those two is achieved in the closed interval between a and b. So that's kind of a cool little offshoot theorem there. And then let's see, domains of functions and their derivatives. If an x value is not in the domain of a function, then it is not in the domain of f prime. Again, the converse of this is not true. It is possible for an x value to not be in the domain of f prime, but still be in the domain of f. Okay? All right. Example 2. Show that these two functions both fail to be differentiable at the origin. Okay, so first off, this piecewise function, in order to show that it's non-differentiable at the origin, I need to rewrite this piecewise, or this absolute value function, as a piecewise function in order to take the derivative of it. The absolute value of x is equal to x for x greater than or equal to 0, and it's equal to the opposite of x for x less than 0. And so in order for this to be differentiable at the origin, I would need the limit, and let's see, how should I do this? Let's do the limit as h goes to 0 from the right of f of x plus h minus f of x all over h. This takes care of the top branch. That's the limit as h goes to 0 from the right of h over h, which is 1. And then if I do it from the left, we've got the limit as h goes to 0 from the left. That's the opposite of x plus h minus the opposite of x all over h, which is the limit as h goes to 0 from the left of negative h over h, which is negative 1. Okay, so the limit as h approaches 0 from the right of f of x plus h minus f of x all over h does not equal the limit as h approaches 0 from the left of this function. Therefore, f of x is not differentiable at the origin. Okay. All right. G of x equals the square root of x. All right, so let's see. If we try to take the limit as x approaches 0 from the right, of the derivative here, we'll use the f of x minus f of 0 form this time. This is equal to the limit as x goes to 0 from the right of the square root of x minus 0 over x minus 0, which if we simplify is the limit as x goes to 0 from the right of square root of x over x, which is equal to the limit as x goes to 0 from the right of 1 over the square root of x. This does not exist because of the division by 0. So g of x is not differentiable at the origin. By the way, the derivative doesn't exist from the left either because the function doesn't exist from the left, although we didn't even need to bring that into this scenario. Okay, I think I'm a little bit too short of time for our last example, so I'm going to go ahead and cut this video off here and come back with a third video for our final example of this lesson, example 3. Hope to see you next time when we do that. Until then, have a great day and enjoy yourself.